Hey everyone, and welcome to this explainer. Today, we're taking a pretty wild macro to micro journey, zooming from the fundamental building blocks of matter all the way down into the incredibly tiny, perfectly balanced world of atomic structure. If you've ever wondered how the universe actually organizes itself on a microscopic level, you are definitely in the right place. So here's our roadmap for today. We'll kick things off with elements and atoms, head inside the nucleus, check out orbiting electrons, decode atomic and mass numbers, and then wrap it all up with a really fun plot twist, the isotope exception. Let's get right into it.
All right, Section 1, Elements and Atoms, our foundation. You know the drill. An element is basically a substance made up of the exact same type of atoms. It is totally chemically unbreakable. You literally cannot force an element to break down into something simpler using chemical reactions. So the big question is, what actually makes up this unbreakable foundation?
Well, zooming in, we find the atom. It's the absolute smallest actionable unit in chemistry. Really, it's the bedrock of how matter interacts in our universe. But as you guys know, it isn't just some solid, featureless little sphere, right? There is a whole complex internal structure in there. Which brings us to Section 2, inside the nucleus, the heavy center. Now, almost all of the mass of an atom is entirely concentrated right in its center, the nucleus. To put this into perspective, if an atom was the size of a massive sports stadium, the nucleus would literally be a single pea resting right on the 50-yard line. Yet somehow, it holds almost all of the stadium's weight. The particles that make up this insanely dense core are known as nucleons. And inside that dense nucleus, we find two very specific particles. First up, we've got protons, which carry a positive electrical charge. And second, neutrons, which are completely neutral, no charge at all. Together, these positive and uncharged particles huddle tightly together to give the atom practically all of its physical weight. Moving right along to Section 3, orbiting electrons and energy, the outer regions. So, out here in the vast emptiness circling the nucleus, we find the electrons. These are entirely different from those heavy nucleons we just talked about. They're negatively charged, and they zip around the nucleus in specific regions called orbitals. Now, here's a fundamental rule to keep in your back pocket. In a neutral atom, the total number of negatively charged electrons is perfectly equal to the total number of positively charged protons. That precise 1-to-1 ratio is exactly what balances the atom out, so it doesn't carry a net electrical charge. But electrons don't just buzz around randomly in some chaotic swarm. No, they orbit at very specific distances from the nucleus, which we call energy levels. And these spatial rules are strictly dictated by exactly how much energy those electrons possess. The rule of thumb here is simple but absolutely crucial. Electrons further from the nucleus hold more energy. Think of it kind of like stretching a rubber band. The further you pull that negative electron away from the magnetic-like pull of the positive nucleus, the more potential energy it has. And just to give you a real sense of the incredibly tiny scale we're operating on here, let's take a look at the electrical charge of a single solitary electron. It is exactly negative 1.602 times 10 to the power of negative 19 coulombs. I mean, that is a decimal point followed by 18 zeros before you even get to the actual numbers. It's wild, right? It really reinforces how unimaginably small these fundamental building blocks are, even though their interactions literally dictate the shape of our entire universe. Okay, let's test this out with a quick thought experiment. Imagine shooting a beam containing protons, neutrons, and electrons directly past a negatively charged plate. Based on what we know about their charges and masses, what do you think happens? Well, first, protons are going to be attracted to the negative plate because, opposites attract. Second, the uncharged neutrons, they just pass straight through, completely unaffected. And finally, the negatively charged electrons are going to be repelled away. But here is the kicker. Because electrons have the least mass by a long shot, they experience the most dramatic deflection. It's pretty awesome subatomic physics in action. All right, let's move to Section 4, atomic and mass numbers, the math of matter. Let's quickly define the foundational math here. The total number of protons in a nucleus gives us the atomic number, usually represented by Z. Meanwhile, if you take the combined total of both protons and neutrons, you get the mass number, which is also sometimes called the nucleon number. So let's clearly contrast these two critical numbers. The atomic number is protons only. You can think of this as the ultimate identity tag of an atom.
Seriously, every single atom of the same element has the exact same number of protons, and the entire periodic table is actually arranged by this proton number. The mass number, on the flip side, is protons plus neutrons. It accounts for that entire heavy center, the nucleus that we were talking about earlier.
And finally, that brings us to Section 5, the isotope exception, a plot twist.
So, what exactly happens when atoms of the same element don't perfectly match? Enter the isotope. Isotopes are basically atoms of the same element that have a different mass number simply because their neutron count changes. The proton number stays exactly the same, but that neutral weight, it fluctuates.
And this fluctuation creates a really unique dynamic. See, isotopes share identical chemical properties because their electron configurations remain completely untouched. Chemical reactions don't even notice the difference. However, that different neutron count absolutely changes their physical weight, which, by the way, is exactly how technologies like carbon dating or certain medical imaging are able to target specific isotopes.
Which really leaves us with a pretty profound final question. If an atom's heavy core can change its physical weight, but the atom itself remains chemically identical simply because its outer electron shell is untouched, is the tiny, virtually weightless electron the true master of how matter interacts in our universe? It completely reframes how we look at the chemistry of life itself, doesn't it? Thanks so much for joining me on this explainer, and we will see you